In today's lab, we'll be studying RC circuits. And no, an RC circuit does not mean a remote control circuit, but rather a resistor-capacitor circuit. And specifically, we'll be looking at the RC series circuit, which is a circuit that has a resistor and a capacitor in series. And this circuit just acts to charge and discharge that capacitor through the resistor. Now, this process of charging and discharging a capacitor takes some amount of time. It doesn't just happen instantly. And in fact, it actually takes an infinite amount of time. It would never charge all the way up or discharge all the way down. But rather than trying to define that, we can define a characteristic time, or the time constant, tau, that's the Greek letter tau, and we set that equal to the resistance times the capacitance, or RC. So if we take the resistance in units of ohms and multiply it by the capacitance in units of farads, we get the time constant in units of seconds. So if we apply a voltage, V0, across the resistor and the capacitor, then the capacitor voltage will be described by the equation V0, that's the supply voltage, times, in parentheses, 1 minus e to the negative t over tau. So e, that's the natural base, and t is time, and then tau is the time constant, RC. If you plug the time constant tau in for time in that equation, we find that during that time period, the capacitor voltage will charge up to 63.2% of the final value, V0. If you go for 2 tau, then it will charge up to 86.5%. 3 tau will go to 95%, and 4 tau, 98%. So the longer you go, the closer it will get to V0, and technically it will take an infinite amount of time, so it will never actually reach V0. But if you go long enough, then it will eventually get close enough that we can consider it to be fully charged. If you want to discharge the capacitor, then you can replace the supply voltage with a short circuit, with just a wire. And when you do that, then the capacitor will dissipate its energy, it will discharge through the resistor, and the voltage on the capacitor will come back down slowly back to zero. During the discharge process, the capacitor voltage is equal to V0 times e to the negative t over tau. But in this case, V0 is not the supply voltage. It's not the battery voltage or whatever that we connected to charge up the capacitor. Instead, it's the initial voltage of the capacitor just before we started the discharge process. So when you start the discharge, whatever the voltage is across the capacitor, that is our initial voltage. That is V0 in this equation. And t is still time, and then tau is still the time constant, RC. If we plug the time constant tau in for time in this equation, we find that after a period of 1 tau, the capacitor voltage has discharged down to 36.8% of its initial value. If we go for 2 tau, it will get down to 13.5%, 3 tau, 5%, 4 tau, 2%, and so on. So if you wait long enough, eventually it's going to get close enough to zero that we can consider it to be fully discharged. The way this experiment works is we're going to make a simple RC series circuit with a 9-volt battery, a resistor, and a capacitor. Then we'll use the battery to charge up the capacitor, and meanwhile we'll measure the capacitor voltage using our multimeter. Then we'll replace the battery with a wire and discharge the capacitor through the resistor, again measuring the capacitor voltage with the multimeter. Now, multimeters only measure instantaneous values. They don't keep a record over time. But I've got a workaround for that, which we'll look at later. Let's start by finding our resistor for the circuit. We need a 30 kilo ohm resistor. In previous videos, I explained that you can identify your resistor from the color code printed on the resistor, but it will depend on how many color bands are on that particular resistor. The one I have is a 5 color band code, which means I need orange, black, black, red, and then the tolerance. And the tolerance in my case is brown, which is plus or minus 1%. So if you have a 5-band color code resistor, then that's what you need, orange, black, black, red, and the tolerance. But if you have a 4-band color code, you would need orange, black, orange, and then the tolerance. If you have something other than a 4 or 5-band color code, then you will need to look it up and see what 30 kilo ohms is in that number of bands. Anyway, once you've found your 30 kilo ohm resistor, we can use the multimeter to measure its value. As we've done before, let's start by verifying that the probes are in the correct ports. So we want black in COM and red in ohms, so look for the omega symbol. Then 30 kilo ohms is bigger than the 20K range, so we're going to need to go to the 200 kilo ohm range for ohms. Then, as I've shown previously, we'll use the breadboard for this, so I'm just going to put each end of the resistor in its own row, and then we can touch the multimeter probes to either side of that resistor. So we've got 29.9, 29.8, let's see, 29.8 kilo ohms. And I will need to convert that into ohms. We need the time constant in units of seconds, which means we need the resistance and the capacitance in units of ohms and farads. So 29.8 kiloohms would be 29,800 ohms. Then we need our 1,000 microfarad capacitor. And that is this little cylinder. The one I have is black, and then it has two leads coming out of it. The long lead is the positive lead, and the short lead is the negative lead. Now you can also check and see if it has this band on the side. The band is also the negative. So you see it's got like these negatives printed on it. Sometimes it has other things printed on it as well, but if you find this band, that usually corresponds with the negative lead. So long lead is positive, short lead is negative, and you can also look for this band, which is the negative lead. So just pay attention to the capacitor polarity while you're building the circuit. It is important that you put it in the correct way, because if you don't, best case scenario, the circuit just doesn't work. But worst case scenario, the capacitor could explode. So pay attention and just plug it in correctly. Now, unfortunately, these simple multimeters cannot measure capacitance. If you have a fancier one that can, then by all means, measure your capacitor with that. But if you don't have that option, then you'll need to use the nominal capacitance printed on the capacitor. So just like resistors, they have a nominal capacitance, the value that the capacitor should be. So if you look right here, we have 1,000 mu f, that's microfarads, 1,000 microfarads, and that is the value that the capacitor should be. The actual capacitance value will probably deviate from this by some small percentage, just like resistors do, but you'll have to use it anyway for the calculations unless you have a way to measure it directly. Now we need to measure our battery voltage. So as always, let's check the probes. Black in COM, red in V for volts. And then this is a 9-volt battery, so we want the 20-volt range. Then we can just touch the probes to the battery terminals and get the values. So I've got 9.63 volts. So I'll record that as my battery voltage. If the battery voltage is below 8.5 volts, then it's probably a good time to replace the battery. Also, as I've mentioned in previous videos, whenever you measure the voltage on a battery, make sure that the multimeter is set to measure voltage. If you accidentally set it to current and you try to measure across the battery, a large amount of current will flow through the multimeter and blow the fuse. So just pay attention to that and make sure that you're on voltage. Now it's time to build the circuit, so I'm going to do that real quick and then explain after I've assembled it. So this is the circuit. We've got the resistor and capacitor in series with the battery. I've left the battery partially disconnected for now so that it doesn't start charging the capacitor before I'm ready. With the capacitor, I've got the positive lead up here at the top, that's the long lead, and the negative lead is at the bottom of the circuit. The current will come out of the positive red battery wire and flow clockwise around the circuit, which means it'll go from positive to negative through the capacitor, and that's what we want. Now I need to connect the multimeter across the capacitor, and I'm going to do that with some alligator clips. So I'm going to get that set up, and then I'll show you what I've done. Now we've got the multimeter, which is still set to measure voltage, connected in parallel across the capacitor using these alligator clip wires. And I've taped everything down so that it looks neat and is easy to see what is going on. Now, as I mentioned earlier, the multimeter can only measure instantaneous values. It doesn't keep a record over time. But we can get around that by filming it with our smartphone or some other camera. I'm sure there's many ways you could do this, but the way I'm going to do it is I've got the multimeter box with the woodblock and rubber bands from first semester and my smartphone aiming at the multimeter screen. So now when I record a video, it will capture whatever is shown on the multimeter display, and then we can play back the video later to collect the data. The procedure for this is super simple. We start recording a video on our phone, then connect the battery and let the capacitor charge for 2 to 3 minutes. After that, we leave the battery connected and then stop the video. So we start a video, and then I can connect the black battery wire right here into the same row as that green wire. And you can see that the capacitor is charging up. Then we just let it charge up for 2 to 3 minutes and then stop the video. So you'll see now we've already gotten to about 1 minute right now, and it's already gotten up close to 8 volts. So even just in the first minute, it's gotten most of the way there, and then it's going to slow down as we go into the second and third minutes. Now at just past 2 minutes, we've got a little over 9 volts, and the voltage is climbing very slowly. So you could stop here, but if you wait just a little bit longer, it will slow down even more and then stop. So you'll notice here as we're coming up on 3 minutes, the voltage has gotten very close to the final value and it's slowed down significantly. We're only changing about 0.01 volts every couple seconds, so we're almost to the point now where we can stop. And here we are at 3 minutes, so I'm going to go ahead and stop the video, but we'll leave the battery connected. If you disconnect the battery, then the capacitor will start discharging on its own, just start leaking voltage, you could say. So we want to make sure to leave the battery connected for right now. Now, if you're working with a partner on this lab, I would recommend that you export your video to them now so they can start on the analysis while you do the discharge experiment. For the discharging capacitor, we need to replace the battery with another jumper wire. So find a jumper wire that's about the right size so that you can bridge that gap between the two halves of the breadboard. And you'll need to make the switch fairly quickly. If you take too long, then like I said, the capacitor will start leaking voltage, it will start dropping. So you need to pull the battery out and replace it with the jumper wire fairly quickly. So we need to start the video before we do that. So I'll start the video, pull the battery out, put the jumper wire in, and let it go for another 2 to 3 minutes. Alright, here we go. Starting the video, pull out the battery, and get that in there. And now it's discharging. So that was pretty good. I think I did it within a second or two. So if you can do it that fast, then that's about what you want. As before with the charging capacitor, we've come up here on a minute and it's already discharged most of the way. So it was over 9 volts and now we're down to 1.3 something. Now we've gotten to 2 minutes and it looks like the capacitor is discharged most of the way. We're down to just 0.3, 0.2 something volts. And as it goes into the 3rd minute, it's going to continue slowing down, and then we'll go ahead and stop it at 3 minutes. And here we are at 3 minutes, so I'll stop the video. And I probably could have stopped it just a little bit earlier from that, but this is good enough. We'll stop here, and that's the end of the experiment. Now that we're done collecting data, let's turn off the multimeter to save the battery. Also, if you decided to split the experiment differently, where one lab partner does the charging experiment and the other does discharging, then make sure that the person who did the charging experiment also follows the instructions to discharge their capacitor. You don't want to put away a charged capacitor. Now, before I wrap up here, I just want to briefly show you how to get the data from the video that you recorded. If you recorded it on your phone, then you can do it this way by just playing it back slowly in the default video player. I'm going to show you how to do it on an iPhone, but for other phones it should be a very similar process. So what I'm going to do is go to the video, and here at the bottom I can slide through it slowly and look at the time and the voltage. So the time is displayed right here at the bottom of the screen, and then the voltage is obviously on the multimeter display. So all you have to do for the first one is just find right before it started changing. So we'll just keep going here. Okay, so there it changed, so we just go back a little bit, and then this is at 5 seconds. So I would record 5 seconds as my initial time, and the voltage is 0 volts. And then I would go on to a half volt. So you want to do this at half volt intervals, roughly. So here's like 0.45, or we could go 0.56. I think I'll do the 0.45. So I would now record 7 seconds and 0.45 volts. 9 seconds and 1.09. Then we've got 1.49 volts here. That's about 1.5. And this was at 11 seconds. So you just continue this process, half volt intervals, record the time and the voltage. And the time, record it in minutes and seconds, and then later you'll have to convert that into just seconds. And you'll just keep going here until you get within half a volt of your final value. So let's say 9 volts right here, that's at a minute 53, and then I continue at 0.1 volt intervals. So now I need to go up to 0.1 volts, that's at 2 minutes 2 seconds, and then keep going up to 9.2 volts, 2 minutes and 16 seconds, and then 9.3, and that's as far as I can go because that's where I stopped. So 2 minutes and 56 seconds. So that would be my last one, and then I just record the time in minutes and seconds, convert that into just seconds, and then I have a list of times in seconds and voltages. And you'll do the same thing for the discharging video. In that case, you'll start at the high voltage, work your way down at half volt intervals until you get down to 0.5 volts, and then you'll continue at 0.1 volts. So you'll have 0.4, 0.3, 0.2, or whatever until you can't go any farther, you run out of your video. And that's it. So just read your instructions carefully. They will have more information than what is shared in the video. and good luck on your experiment.